Hello and welcome to this video series. My name is Dr. Akram Ahmed and I will be introducing the concepts of artificial intelligence, and in particular today in this video we will be talking about the Perceptron algorithm. Let's start. So, Perceptron algorithm is one of the type of supervised learning techniques. What is a supervised learning technique? A supervised learning technique is something that you supervise and you tell the computer and train it basically first and then ask it to predict. To understand how this technique actually works, let us take an example. And in this slide, the example is about predicting the weather. And we would like to predict in particular, is it raining versus is it not raining? Okay, so we want to predict if it's going to rain tomorrow or if it's not going to rain tomorrow. And that's the prediction that we want to make. For that, we have to collect some historical data. So we take some historical data and then we have to label it. What does labeling mean? So the historical data that we might collect might be a temperature, humidity, pressure, whatever that is required to predict whether it's raining or not. And then we have to label it. We have to tell it this point or this set of data for the temperature and humidity, is it going to rain or is it not going to rain? So we take the temperature and humidity and we actually observe that day, for example, did it rain or not, and then we classify it accordingly. If it rains, we classify it as rain and we label it as rain, and then if it didn't rain, we label it as it did not rain. Okay, and we need to collect all of this data for the past and for the history, and then provide this data for the computer in the hope that the computer can actually learn from this and can actually predict what tomorrow is going to be. Okay, so the question is, can we produce a function or a model to predict the weather? Okay, predicting the weather is nothing but classifying, in our case, is it going to rain or is it not going to rain tomorrow? So that is basically the classification we want. So the classification is rain versus no rain. And the question is, how many classes do we have? So the first question that we should start with is, how many classes do you have so that the Perceptron algorithm can distinguish between them? And in our case, we only have two classes. The first class is rain and the second class is no rain. So in the Perceptron algorithm, we want to predict the weather. What we do is we go ahead and collect the data. So this is the data that we have collected. Suppose we collect this data, the humidity and the pressure. Okay, and these are what we refer to as features. So we collect different features, and these features, what we go is we at that day identify a label for it, whether it is raining or it is not raining. So we collected this data and that day it rained, so we label it as rain, and then for another day we go ahead and collect this and label it as did not rain. The other day was not raining, then the third day it was raining, and so on. We collect all the historical data. So we need to get features. Now in this example in particular, we only have two features, the humidity and the pressure. But in real life examples, you might have multiple data. We will just take the humidity and pressure for simplicity because it makes the idea simpler and you can actually work with this and understand the basics. Then you can actually map it to anything else. So what we want to do is we want to produce an estimate, and basically what we want is a function that takes an input as humidity and pressure and generates for us the class or the label that we want. Okay, so this is what we want. If I give you a pressure and the humidity of certain values, so if I give you two numbers corresponding to the humidity and pressure, so if I give you 79, 1031, I want you to tell me that it is raining. Okay, that's because that's what data is proposing. Okay, or if I give you a number that's very close to it, I also want you to tell me that it is raining. Okay, and we want the computer to do this seamlessly without us interfering in it. So if you give it F93 and 999.7, it should tell us it's basically raining, and if you give it this, it should tell us there's no raining, and so on. And this is what we want the computer to do using the Perceptron algorithm. So in the predicting weather, we first need to understand the data ourselves because we are the ones who's going to tell the computer how to predict this data. So what we do is we use our visual perception and we plot the data so that we as human beings first can understand what's going on so that we can actually tell the computer to do it in the same manner. So if we plot the data that was on the table, so suppose the plotting of the table, we get the humidity and the pressure, and we get these type of data where the blue point over here represents a data set that we have actually gathered, and it corresponds to a rainy day. So it is raining over here. And the red data set over here is basically no rain. And I actually plot the rain and no rain data based on the humidity and the pressure on this. And I then try to come up with a method where I can actually distinguish between rain and no rain, and that's what the Perceptron algorithm is supposed to do. So if we have a set of data like this, there are multiple ways of classifying whether a new data point, when it comes, it's going to be raining or no raining. So suppose a data point that comes over here where my cursor is now, you can clearly say that this is a raining situation, whereas if the point is over here, you could clearly state that this is a point where there is no rain, so most probably it's not going to rain. So for this data, we would like to have some sort of method that can classify the data, okay? And that's the aim of our Perceptron algorithm. Okay, there are multiple approaches, and the Perceptron algorithm uses something called the decision boundary. It basically makes a boundary in the data, and if it's above that boundary, it's one class, and if it's below that boundary, it's another class. And if you look at this data, where we have cleaned this data, and this is what we call the linearly separable data because there is no overlapping between the data, it is very easy to come up with a boundary that will predict whether it's raining or not. And that boundary, as you can see, is a line that can actually separate between these two. So this line could be a good way of predicting whether this the new data point, if it lies above this point, it will be no rain, and if the data point lies below the point, it is raining. So this is what the decision boundary is, and this is what the Perceptron algorithm is gonna try to predict from the data that we have given it, from the labeled data that we have given it. And the question then becomes, can the Perceptron algorithm come up with this line without us interfering in it? So we just give it the data and it can learn and bring the line by itself, and that's what we are actually after. Okay, so the Perceptron algorithm is trying to find the line that can classify the data correctly. Okay, so here is the line. Okay, so if a new data comes over here, you can basically say, since I am above the line, I'm classified as no rain, and if I'm below the line, the point that signifies over here, that means I am not raining. So what we need to do is to find this line so that we can separate the two classes 0 and 1, and we want that to be seamlessly done without us interfering with the computer by just giving it the labeled data, and it comes out with this line by itself. So how can we do that? So there are several algorithms that can be used. Okay, decision boundaries in 2D is a line. Okay, and in 3D this will become a plane, and in upper dimensional 4D, 5D, 6D, since we cannot imagine it, we will be referring to it to a hyperplane. Okay, so a hyperplane is some sort of a boundary in an n-dimension space that is basically separating my data. Okay, so in 2D it's going to become a line, in 3D it's going to be a surface that is basically separating something from the top and bottom. So it's a surface, okay, might be straight surface or bent surface, and we would call it a hyperplane. Or generally anything can be actually referred to as a hyperplane. Even a line and a plane can be actually referred to as an hyperplane because that's a general case. So any n-dimension data would have a hyperplane separating the data of the classes that we want, and we would like to have a good separator. Now we can have good separators and we can have bad separators. Bad separators will not be capable of classifying the data that we have correctly, and a good separator would actually classify the data that we have in a very nice manner. Okay, but the problem is, and in the real life, that the data that we get is not very nice and clean, and it's not linearly separable. You can see that there's a point over here and there's a point over here that are not linearly separable. Okay, so you cannot find a single line that can separate exactly the data into two different classes, but we want to find a line that works most of the time, and then that's how we human beings actually function also. Okay, is the shown line the best one? No, it's not the best one because there are few classes over here that are not, but it works pretty well. For most of the time, it's going to predict correctly. It'll be a few times that it doesn't predict correctly, but based on the data that I have, this is not going to be an issue because this is the most I can do with the data that I have. Now, of course, if I add another feature, it's going to become a 3D, so it's going to become a hyperplane, and in that case, you might be able to get something that is better predictor because you have more features, and that is why we collect more and more features so that this data becomes separable. However, how many features do you try to measure? We cannot measure all the features. And that is why we revert to few features and then we allow for some sort of an error and we accept that. And that's what happens even with us human beings. When we try to take a decision, predict tomorrow what's going to have, with all the expertise that we have, the expert might fail in predicting the weather tomorrow, okay, or maybe after a week or a month. Okay, so all of this is something that is natural in artificial intelligence. And you need to know that it's not perfect. It is actually trying to mimic the human behavior, and it's trying to work with the data that it has and try to predict the best thing it can. Okay, so it's a best effort that it's trying to get out of it. Okay, so there are multiple lines between the two classes that we have, as is shown over here. There are multiple lines that we can come up with, and we want the Perceptron algorithm to reach to a line, okay, and we'd like it to be the best line if possible, but it's not necessarily the actual optimum line, but we want to find a line that can separate. So whether we find this line or we find this line, since both of them are separating the data in a nice way, well, we are going to be happy with that in the Perceptron algorithm. Okay, so we want to find a decision boundary. So in the two cases, in the 2D cases, what we have is x1 and x2, which is the humidity and the pressure. And what we want is a function, okay, so this is an edge function, it's an hypothesis function. So we basically want to give it the x1 and x2, and we want it to tell us, is it going to rain or is it going to not rain? And how are we going to do that? What we're going to do is we're going to take the x1 and x2, and based on the x1 and x2, we will find some weights, which we multiply it by this x1 and x2, so that it actually can predict whether the it's going to rain tomorrow or not. And then based on this data, based on these weights and the input that was provided, we are going to check if this is greater than or equal to 0, because that is going to be representing a line. And if you look at this equation over here, this is nothing but an equation of a line. Okay, so we actually have W0 plus W1 x1 plus W2 x2 is nothing but an equation of a line. You can actually rearrange this and you can make it in the form is y is equal to mx plus c. But we have reformed this line or this equation, and we've written it in this way mathematically. And we say if this point, if the point lies on the line, that means if the point that we have was on a line that we have for the perceptron, it is going to produce a 0. If it was greater than 0, that means it's up over here, and this means that this is going to be if it's greater than 0, it's going to be down here, it's going to be rain. If it's less than 0, it's going to be up here, which means it's no rain because the line is tilted this way. Okay, so what we want to do is we want to come up with this weights, okay, such that when we multiply the weights with any input that has come based on this, and we compare it to 0, we can say it's raining or not raining. So this is basically what we're trying to do. Find the line, and we look at if it's below the line or above the line. If it's below the line, which is represented over here by x, by the weight multiplied by the x is greater than 0, and then say it's raining. Otherwise, we say it's not raining. So this is the thing that we would like to do. Okay, and instead of rain and no rain, what we usually do is we abstract the concept and we say we label the data instead of rain and no rain into 0 or 1. Okay, so most of the time we use 0 and 1, and this 1 means it is going to rain, and 0 it's not going to rain. And we mathematically over here are trying to make the definition more rigorous, and we define everything as a vector, okay? So the vector, and we have two vectors over here, x and w. X is nothing but our input, which is x1 and x2. These are the inputs, and the w vector is nothing but w0, w1, and w2. These are the weights that we would like to predict, and if we can predict these weights correctly, then we can predict a line over here that is basically separating the rain versus no rain, okay? And for the x, since w is coming to be having three weights, which is w0, w1, and w2, we could actually add 1 over here, which does nothing. So multiplication by 1 does nothing. So we add 1 over here, and the result of this, to find the equation of the line, we can represent the data as w dot product with x, where w and x are vectors. When you do a dot product between two vectors, you get w0 plus w1 x1 plus w2 x2, and this is nothing but the equation of the line that is representing by one of these yellow lines that's in the middle. Okay, so we have taken what we wanted to do. We wanted to find some weights and then multiply those weights with the input that we have, and the result of that, we compare it to 0. Okay, so if it's on the line or above it, then we basically want it to be classified as 1, which is rain, and then otherwise it's going to be classified as 0. Okay, so this is how we mathematically represent, and we broke down the problem that we had. We looked at it like this, and then we made it into a vector multiplication. Okay, so there are two vectors, w and x. And we said in the x, the first one, since we only have two values, it's 2D data, and the weights have 3, so we have this is what a constant that's been added to the line, so that we can actually control the line and how it moves. So what we want is basically find the w's such that when we multiply these dot products, we get this equation, and for that we had to put this as a 1. So this is where the 1 is coming from. So you multiply this by w0 and you get this, and you multiply x1 by w1 and you get this, and you multiply x2 by w2 and you get this. So this equation is basically represented by the dot product over here. Okay, so that's what we were trying to do. We want to find a function, a hypothesis, from which we give it x1 and x2. It's going to take the x1, x2, make it a vector, and do a dot multiplication with w, multiplied by w0, w1, w2 accordingly, okay, and get this equation. And then we find if I am greater or equal to this equation, that means I'm going to be having a rainy situation, which is 1. Otherwise, we're going to have 0, which is no rain. Okay, so that's the intent of what we want to do. Now the question is, how can we actually do this? Okay, so this is another slide where we are just showing that you could actually replace that by a vector multiplication. And in the vector multiplication now, notice how abstract this has become. It's only weights multiplied by the inputs, and you get it if it's greater than 0, that's 1. Otherwise, it's going to be 0. And now it becomes pretty easy to think of it and try to solve it. So in the Perceptron algorithm, there is something called the Perceptron learning. And we'd like the algorithm to learn and tell us seamlessly, without us interfering, that, hey, this is a good line that you can actually use to classify the data. So look at this. This is the line that the Perceptron might come up at the end. And this is a good line, although there are some misclassification, but you would agree that this is a line that is, for us human beings, even if we look at this data, this is a good enough line to classify the data. There are some errors, but we can live with those errors, okay? So how does the Perceptron learn? We give it the point x and y, and what we do is we want it to learn from the data. So what happens is that the Perceptron algorithm starts with a line at random and then utilizes the data that you have given it, and then shifts this line from one location to another until it finds a line that can classify the data. To shift the line, it has to learn. And to learn, what we need is to update the weights. The learning is only going to happen to the weights because x is the input, so we cannot change the inputs that are coming. This is the value of the pressure and humidity, whatever that we have read, so we cannot change that. So the only thing that we can change is the weight. So what we try to do is update the weight and try to get a function out of it that would basically learn. So the function that we have come out with is we take the weight, okay, and the new weight is nothing but the old weight plus some value alpha, this is called the learning rate, and then we multiply it by the output that we have minus what we have predicted. Now notice this is HW of x, this is our function that we were talking about in the previous slide. So this is our prediction of the data, and then we multiply it to the xi. So we update the weight based on this, and this alpha is a factor that is telling me how fast do you want to learn. So you want to be learning very fast and converging to this point very fast, or do you want to go slow? And we'll talk about the alpha in a few minutes, and we'll elaborate it. But this alpha is always a number between 0 and 1. Okay, so what we want is we want the actual value and our predicted value. We want to subtract them, and we want this to be 0 for the training data that we have. Okay, and to make it reach to 0, if the weight was not the appropriate weight, we want to shift the weight. Now notice, if all the values of x were positive, if I have an actual value and my predictor is smaller than the actual value, so this will become a positive number because my actual value is larger than the predictor value, and this will actually increase the weight so that the weight can actually rise to the level that we want. And on the other hand, if the predictor was smaller than this, and given that this is always positive, what will happen is that this value will become negative. That means my predictor is predicting a higher value, and I want to decrease the value of the weight so that I reach the exact prediction that I want. Okay, so that's the notation, that's the notion behind what's going on over here. And then how fast do we want to bring this to the actual weight? We control it by alpha. So sometimes, due to outliers that are there, we do not want this outlier to basically come up with some or change our data so much that we start misclassification. Okay, so for example, let's suppose that we have a point over here that said it is raining, and if we have this line and we use that outlier that is over here for raining, what will happen is if we shift the entire line over there, we will have all this data being misclassified. So all this data that is red over here will become misclassified. If to limit that, what we do is we use an alpha to be a small number. And when we use it to be a small number, what happens is the shifting doesn't happen too much. So we might move only 10% or 5% or 1% of the distance that was supposed to be moved. And that outlier then will not affect too much. So if we select all the data and train on it, for example, so that outlier will pull this to the to go a bit up, but it will not change it too much. Okay, and this data will also pull, so all of them will pull down, and we're going to move 10%. So on the average, we're going to be going down, and the outlier that is over here will have lesser effect. And that is why we have this alpha. Okay, so we're predicting over here, and we would like to find and update the weights based on this equation to come up with the best line that we can to separate the rain versus non-raining data, or the classes 0 and 1. Okay, so that is the gist of this algorithm and what it's trying to do. So Perceptron learning rule is, again, as I told you, it's the actual value minus the estimated value, and then we are trying to control how much movement of this line is happening with the alpha, and we actually update the weights based on this. So we take the old weight and add to it the alpha multiplied by the actual value minus the estimated value. This will tell you whether you have to increase or decrease the value, then multiply it with x, and based on this alpha, this is a percentage of how much you want to add to this weight, and then we update that weight individually. And notice this is WI. We have to repeat this for all weights. So we have, for our example, we had W0, W1, and W2. We have to repeat this for W0, and then we do it for W1 and for W2. So for all weights, you have to do this update. Okay, so if the actual value was greater than the estimate value, the weight update is positive, given that the x is positive. And the other statement is that this value will be negative if x was positive. This value will become negative if my estimate was higher. So this is how it is going to bring the thing to the actual value, okay? If it was equal to 0, then I have to do nothing. So notice if it was the actual is the estimated, this becomes a 0, and anything multiplied by 0 is 0, and the new weight is equal to the old weight. That means that I have reached to the value that I actually want. Okay, so this is the notion of how the perceptron algorithm works. And this is how a complete journey of a perceptron algorithm. You start with a random line, so you start with a random W's, and the random W's, when you multiply them with the inputs that you have, you will get a random line. Now this random line could be here, could be here, could be here, could be anywhere. We are taking this example where there's a random line, and then what we do is we pick a point, okay? So we pick a point, for example, this point, this is the point that we picked, okay? And then we train and we move the line above this point, okay? So it's misclassifying because this line is classifying the top thing as red and the below thing as blue. So we move this line upwards, and it's going to go up and then try to classify this point correctly. Then we're going to pick another point, and suppose we pick this point, then this line is going to be moved and shifted upwards and tilted also at the same time, so that we can classify this point correctly. And going on, if we select all points, eventually what we want to do is to reach this point. Now in this point, notice in this line, if I pick any red point, it's going to be classified correctly. So it's in the red region because this line on the top of this line over here, it is the red, and then below the line is blue. So it is classified correctly. So in this case, in this case, in this case, whatever I choose from the red, it's not going to move the line because things are classified correctly. So the actual label is the predicted label, and that will not change the line. That line will only change when there is a blue that is not classified correctly. So that is why for the first time, when we select any red, the line is not going to change. But if we select one of the blue, the line is going to change. And in this example, the blue that was selected was here. Then if we select any red, it's not going to change. And if we select this blue, it's not going to change. But we select one of these 4 blues, the line is going to change. And in this particular example, we selected this, so the line became here, and so on. As you can see, these things are going to change. And what's going to happen is, at the end, when you reach to a line that can separate both, the predict and the actual will become equal. So the predicted class will be the actual class, and no matter what point that you actually choose, the line is not going to change it. That is when we say the algorithm has converged, okay? So it is not moving anymore, or the movement is pretty small, okay? Compared to it, compared to the movements that was happening before, okay? So this is the perceptron algorithm and how it works. And here is a representation of how it's done mathematically. So what we have is nothing but the sum of wi and xi. This is nothing. If I just write it down so that you guys don't get into what we had is w0, okay, plus w1 multiplied by x1, and then we had plus w2 multiplied by x2, okay, and we can represent the entirety of this into something like this as a summation. So don't be afraid of what you're seeing over here. This is exactly the same as this, where n is nothing but 2. So we start with 0, and what happens in 0 is that we have w0 and x0. x0 is nothing but 1, and w0 is going to be given to you. So notice this is what we get, and then we have w1 x1, so this is there in the next term, and then we get this. So this is nothing but a representation of this equation, and we would like to say find the hyperplane. Notice, because we have n dimensions over here now, and in the general case we say we want a hyperplane that we can have this to be equal to 0, that perfectly separates the two groups. This is what we want to do, okay? And note that w is nothing but this, can have n features, and for each feature you will have a weight, okay? So it's nothing but a vector, and this vector is going to be always orthogonal. It's going to have a 90-degree between it. So this is the vector w. You can see the vector w here, okay? So this is the vector w. Vector w is going to be always orthogonal to the line that we have, okay? So when we start, we can start with this orthogonal vector in a random place, and then we can actually train it. And what we want is, we want to multiply w by x is the dot product. It's nothing but the absolute value of w into absolute value of x into cosine theta, and this is basically the projection of that onto the other one onto the other. And what we want to do is move this so that the weights are maximized. Okay, so how do we do that? We go through an algorithm, and in this algorithm what we do is we have t training points. Okay, so we have t training points. Yeah, so we have point x0, y0, x1, y1, xt, y until xt, yt, and we have inputs. Okay, so this is a training instances. So this is how many times we want to train, how many times we're going to train the algorithm, and then we need xi, these are the inputs, and yi's, these are the corresponding actual correct labels or classes. It has to be the correct one. We need it so that the algorithm can learn from it. And then the output is then the W. Okay, so we want to calculate the W, and in this what we do is we loop on all the sample points that we want to train our algorithm on. Okay, and we go from 0 to n, and we have the J is basically controlling how many weights do we have. Okay, so and then the weights are going from 0 to n. Notice how we have 0 to n weights over here. So we go from 0 to n, and we update the weight based on the same equation that we have just spoke about. So we choose an alpha. So alpha could be a number between 0 and 1, and then the output label, the actual label minus the predicted label, we just subtract that and we multiply that by the x of I, and we update it. And this is an algorithm that will run. It's going to update all the weights. Okay, for each point, notice it's going to update all the weight, then it's going to pick another point from here and then update the weights, then pick another point from here and then update the weights, and it's going to do it for all the points t that you have for the training and update the weights, and hopefully at the end you will have a line that has that is in a good place to classify the data that you have. Okay, so that's basically what's happening in this. And that's what's happening over here. So you start with this. Okay, for example, you have this line. This is the red line, and you have the W, which is this one. Okay, so this is the W, and what you can notice that this random line misclassifies, okay, the data, because the 1 is above, okay, which is the blue, okay, and 0 is red, has to be below the line. So it has to be below the line. So W always points to the 1, which is the blue. Okay. So as you can see, there are multiple points that are misclassified over here. Okay, so these points are classified as blue from our classifier because the line is going from here. So it is actually red, but our classifier is classifying them as blue, and that is wrong. Also, we have this point that is classified as red by our classifier, but the actual label that it has, it was blue. So our classifier is not a good classifier for this data. This is a random classifier that we started from, and now we need to update the weights. How do we update the weights graphically? So we talked about it in the algorithm. Now let's talk about it graphically. So what happens is basically we pick a point. So we pick this point, for example, and we train on it. When we pick this point, what will happen is that the actual minus the predicted will not be 0. Okay, so this is a label 0 and this is a label 1. So actual is 1 and the predicted is 0. So 1 minus 0 is 1. So my algorithm would know that I have to increase the weight somehow. And to do that, what it's going to do, it's going to increase the weight. And when it does, it's going to have changed the vector to this position, okay, the W vector. And notice the line is always perpendicular to this vector. So it was in this position. So this was the old position. And now it is in this position. And the line would be something like this now, okay, so somewhere here. So notice when we update the weight, the vector shifts. And when the vector shifts, and it's perpendicular to the line that is classifying, it actually shifts the line with it. And when it shifts, it will be classified correctly, and that is what happened over here. Okay, so the next one is we had this point that was misclassified. Okay, so we could actually take, so this line is predicted by this point. Okay, then this point is misclassified. If we take this point and train on it, it's going to go and change the W vector that is over here to a new W vector. Okay, so it has to go, and we have misclassified this, and since we misclassified it, we update the weights, and we get the new vector that is over here, and the line shifts. Notice the red line that is over here now is the line that is trying to predict, and it actually classified this point correctly and then all the other points correctly, and that's what's happening graphically in the vector space. Okay, so the W is shifting, and it's basically trying to predict whether it's a red or a blue. Okay, and the training is happening, and what happens at the end of the training, that we get a line that can actually classify the points. Okay, and after this, if we train, the actual minus the predicted will always be 0 because all points are correctly classified. So no matter how much we train, how much data points we give it, it's going to stay on the same line. Okay, so let's take an example. The example over here, so suppose that we had to train a perceptron with the following data points and corresponding labels. So these are the points. So we have 1, 1, and the label is 1, whatever the label is. It might be rain, no rain. It might be tomorrow is going to be school day versus no school day, based on the rain. Or you might have different classes. For example, tomorrow are you going to be sick versus no sick? Any label that might be. Are you going to be traveling, not traveling, based on some certain behavior that you have in your job, whatever the data it is. It could be label 1, and then P2, this is the point, and it has a label of 0, and then P3 has a label of 1. Okay, so these are the coordinates, and these are it. And the algorithm picks for training, these are points, it picks 1, 2, 3, then 1, 2, 3 again. Okay, so it's going to pick these points in this specific order. Okay, and it's going to try and predict a line that can actually separate the two classes. So, well, moreover, the initial weight vector is given over here. Okay, and this is what we're going to do in the exams. We're going to give you the weight vectors, and we're going to give you the sequence of points, and then we ask you to train, and we see whether you understand how the perceptron algorithm works or not. Okay, and notice over here the alpha, and we said that alpha is going to be small. We always choose it to be small because we don't want outliers to basically affect too much of our data. Okay, and outliers might, if we keep it 1, the lines are going to shift too much, but if we keep it 0.1, we are shifting it a little bit less. The caveat of having this alpha is that you might need more epochs or more iterations or more loops to come to a good line that separates the labels that you have. But that is something that we could live with. We can ask it to train, instead of training on 10 points, we can ask it to train on the same points 50 times. Okay, instead of so use each point 5 times, and then we can actually have alpha to be 0.2 or 0.3, and then since we are training on the same point multiple times, it is going to move, and we pick the points randomly then. Okay, we don't pick it in sequence, we pick it randomly, so that the randomness is gonna most probably not select the outliers more than the others. Okay, so if it was purely random, it's not going to select, and the other points will actually pull it towards itself, and the outlier will not. So that is why we have the alpha to be 0.1, and in this example we will take it to be 0.1 just for the sake of simplicity. Okay, and to do this, okay, what we want to do is we want to find what will be the value of W after we do this training. So we have training what, P1, P2, P3, then P1, P2, P3, and we want to see what is the update that's going to happen on this vector when we use a learning rate of 0.1. So let's do this example. So in this example, we start with W's, and we make this table, and we make W0, W1, W2, the values that were given in the question. So this is the values. And then what we do is we take the first training point and put it over here. And that's 1, 1. Okay, so that's the first training point, and we put the actual label with it also. So the label of this data, the actual label of this data is 1. Okay, so once we put this, we have to fulfill all the rows in the table, we need the value of x0, and the value of x0 is always set to 1. As I told you in the previous slides, the value of x0 is always 1 because there is no x0, we have x1 and x2. So what we do is we put 1, and then what we do is we predict. Okay, so we cover this data that's over here. Let me just highlight it. So I'm just going to use a green color to cover it, and then I'm going to erase the green color. I'm going to hide this, and I'm going to predict. So if I have x0 to be 1, x1 to be 1, x2 to be 1, what is my predictor, which is having the value of w0 to be 2, minus 1, and 1, is going to predict. So what I'll do is I'll multiply 1 by 2, and that's what's happening over here. Okay, so I'm going to take the yellow one over here. I'm going to multiply 1 by 2 over here. So I multiply this 1 by 2. Then I'm going to multiply this 1 by this minus 1. Okay, so minus 1 multiplied by 1. And then I'm going to multiply this by this. Okay, so 1 by 1 is nothing but 1. Oh, sorry. So this was the 1 and minus 1, and this is the 1 by 1. And then the result comes out to be 2. And 2 is greater than 0. And greater than 0 means a label of 1. And then we look at, is it matching what we have? So we actually go over here and we see, is it matching what we have over here? And yes, it is matching. Since it is matching, that means I have classified this correctly. And I do not need to update the weights. So what we do is, the target is 1, the predicting is 1, there is no update. I copy the value of W0, W1, and W2 downwards, and I say no updates. Okay? Because my predictor actually predicted the same thing as the actual. Okay? So the target was 1, and we got predictor of 1, we don't do anything. Let's take the second point now. The second point was 2, 4, and notice we add the 1 over here, and it had a label of 0. And now when we do this, notice what's going to happen. We multiply the 1 by 2, the 2 by minus 1, and the 0.4 by 1, and we add them all together, and we get a 0.4. The 0.4 is greater than 0. Okay? The greater than 0 means that my predictor is predicting it as label 1, where the actual label is 0. Okay? So now I have to update all my weights. To update all my weights, what do I have to do? I have to take the old value of the weights, multiply alpha, which is 0.1 over here. Notice the alpha, I just copied it over here, is 0.1. And the actual minus the predicted. So the actual was a 0. And minus the predicted. Okay, the predicted is coming to be a 1. So that's what I predicted. And I multiplied by x. Okay, so this is the general rule. Okay, and we could actually see over here that this is nothing but w multiplied by 0.1x minus 0.1x. So simplify this. 0 minus 1 is minus 1. So the minus, and then you can actually do the mathematics and get to this equation. And then we update w0. W0 had a value of 2, so we write 2 over here. And then we minus from it 0.1, that is what was the equation, multiplied by the value of the x1, x0. So x0 had a value of 1, so we multiply by that, we get a 1.9. We take w1, we take the value of it, which was the old value, and subtract from it 0.1, okay? And then multiply it to x1, and that is the value of x1, which is 2. So you get a minus 1.2. So notice the new value of w is minus 1, or w1 is minus 1.2. Similarly for w3, we multiply the 0.4 over here with the 1, okay? And you get a 0.4, and then you take the old value, which was 1, minus 0.1 of the value that you find, and you find it to be 0.96. So these are the new updated value of W0, W1, and W2. And what we need to do is we need to change these values here and say, now my vector, the weight vector, has updated itself. Okay? So because there was no match between the actual and the predicted. Okay? And that's what's happening. And notice now the weight vector changed, and the weight vector will change the line with it, and this will become a better predictor for my class, okay, for the different classes that I have. And then you repeat this thing for the third point, and for the third point you have it minus 2, 0, and this one you have to put by yourself, and the actual class is 1. When you calculate, you find that the value is greater than and 0, and that means that it is a label of 1, and the actual label was 1, so there is a match, so there is no update. And then you keep on doing this for the rest of the table, and you can actually do this on your own time. I've just given all the calculations over here so that you can do it. You can pause this video, or you can go to the slides and you can read it out. What I would recommend is delete these information and try to do it by hand so that you get the practice of it. Okay, and you would see that there are no more updates that are done when you do the calculation, so that always the predict is equal to the class that was the actual class, and hence we have come to the best line that can separate the data that we have with the labels that it has, and the algorithm should stop. Okay, so it will stop after these lines. Okay, so what we did over here is we said that we'll come up with a line, and we will have a decision if something is above this line is going to be class 1, and it's below this, if it's above and below, it's class 1 and 0, depending on which classes you're pointing towards. And this is what we call a hard threshold. And this is like what's happening. If you multiply the weights, okay, if the point you multiply the weights and the value of the inputs, and you find it to be the Wx, you find it to be less than 0, I want you to put me for 0. Okay, let me take a pen over here. So I want you to put me over 0 over here. Okay, so I want you to be putting me over here. And when the value is showing me it's greater or equal to 0, I want you to be giving me a 1 over here. Okay, so this is what's happening. And this is what we call a very hard threshold. So anything that is above or below, it's classifying. It's a good classifier if we want to just to know whether it's raining or whether it's not raining. So it's a good classifier telling me all of this information. So this is what we call a hard threshold. But most often in most of the application, we would like to know how confident I am in the prediction that I'm doing. Okay, and this hard margin that's going from 0 to 1, whether you are above or below, doesn't give us that feel. It just tells us that, hey, I am raining or I'm not raining. It doesn't give us anything else with it. For example, over here, let's take point 1 and point 2 that is shown in the slides over here. Okay, so point 1 over here, it is classified as being raining, but as you can see, since it's very close to the line, if I ask you, how sure are you of this thing? Are you very sure that it is going to rain? You might get a second thought over here and say, well, it's very close to the line, and this line is not 100% accurate, and yeah, I'm not very confident over here. Versus this one. Okay, so if you look at this one, if I tell you, is it going to rain here? You would say, I'm like 90% confident, on 95, maybe even almost close to 100, that it's going to rain based on the data that's there. Okay, so the level of confidence that you will have on the point number 2 is going to be quite higher than point number 1. And the hard threshold doesn't give us this feel. Okay, and that's why people went to something called a soft threshold. Okay, and in the soft threshold, what they did is they made a function that goes from 0 to 1, and it's a smooth function that has a value. Okay, and in this smooth function, it's going to tell us, it's going to return a number for us, and that number might be something that we can actually use. So, for example, if we use this soft threshold and we get the value is for this 2, it is going to be something like over here, and I tell you it's 0.99%. So you'll say, well, yeah, it's gonna rain with a very high percentage. Okay, I get some probability or some insight information with it. When I give you the 1, well, is it gonna rain? So it's gonna be over here. Maybe it's 70% or 60%, whatever the percentage is. It's above them 50% because it's below the line. But you come and say, well, I'm not that sure. I'm going to be 50% sure that this thing is going to rain, or 20% sure, depending on how you actually set up your confidence level with this information. So it will give you some sort of a scale with it, and that scale is going to give you a better insight of the data. So you know now, well, the confidence is pretty low or the confidence is pretty high of what am I doing. Okay, and that data could be actually used by experts. For example, so if a surgeon was doing some sort of surgery and an AI was telling it, you wouldn't want a hard threshold telling him if he's doing a brain surgery whether this thing is okay or not okay. You want to give him some more information and say, well, this is okay, and I have very high confidence if you do the next step in the procedure, the patient is not going to be harmed. But when he comes to a sensitive area, for example, you might want, which is very close to the boundary, you might want to tell the surgeon, well, you can go further, but the confidence level is quite low now. Okay, so the surgeon now, he has to jump in and use his real intelligence and decide whether he actually wants to go and do this, or it is too risky to do whatever he's doing. Okay. So this is again something that's used. Another example is if you're going to the desert and you're going to camp and it's going to rain tomorrow. Okay, so when that in the desert the waters might form streams, and you are going to a place where streams might be formed. So if the chances were 90% for tomorrow to be raining, you might double think of where you're going to camp in the desert. Okay, but if the chances were like very little, okay, 1%, then yeah, okay, so yes, I am close to the decision boundary, but the chances are 1%. You shouldn't go, but you might opt to take a chance and do it, although that's something that I don't recommend. So that's the type of thing. So it gives you some more information about what is happening with the threshold, and it gives you some confidence. So I hope that you have understood what is the decision boundary and how the perceptron algorithm works. The perceptron algorithm at the end only predicts a line, and that line uses the label data to train itself and come by updating itself. We went to the updating by using the learning rate alpha and the actual weight and the actual class and the predicted class, and then it trains itself and comes without human beings interfering and comes to a line that can predict. And then we can utilize that line later on when we get data to see whether this thing is good enough or not. Okay. At the end, I would like to thank these people for contributing in this in the slides and the material that we have made. And I hope you enjoyed this video. Thank you very much, and bye-bye.